talking about the virtualization environment in the last couple of weeks, and hopefully you built your virtualization environment by adding an ESXi server and the vCenter server. And obviously we've created a virtual machine as part of that process just so we can see it working a little bit. But obviously in a real network, there's probably more nuances than just a simple network. Okay, so on a production network, you might have multiple subnets for multiple purposes. You may have, if I give you the example of TFSA, we might have an individual subnet per classroom, or at least a different network for the student network versus the lecturer network versus the server network. Maybe the Wi-Fi network is different as well. Maybe, obviously, there's the internet connection. So how do we get our servers on our in our virtualization environment to be able to service the clients in the various networks? We talked about initially in the week one about the different the number of network cards we need for the purpose of actually management for actually VM traffic. So the term VM traffic is referring to traffic that's going to the virtual machine and coming from the virtual machine to the physical network. But we also need it for things like vMotion, which is that live migration, the DRS, the fault tolerance, the high availability, and we also need it for the storage, and we also need it for the management. Some of these networks can be shared, obviously. Okay, you don't have to have a separate network for each one of those things, but you can share some of the functionality for both networks, but some can't. So the ones that have higher traffic demands, such as the storage, such as the VM traffic, shouldn't be shared with anything else. They should, in fact, have multiple network interface cards so you can actually load balance between them, as well as providing fault tolerance if one of the interfaces fail. So let's go into the networking. So today we're going to identify the components of a virtual network. We're going to create some virtual switches. And we're going to create some distributed switches. And we're going to look at the, we're not going to use the Cisco Nexus 1000V, but we're going to talk about the Cisco Nexus 1000V virtual switch. All right, so and also we're going to be creating and managing the NIC teaming, VLANs, and private VLANs. So hopefully all of you guys should have already done some Cisco. Okay, you've done your Cisco routing and switching yet? You know about VLANs, correct? You know about trunking ports? You know about the reason why we have trunking ports, right? Between VLANs? Okay, so those are the things we're going to assume. So we'll be also looking at configuring this switch security policies. Did that just jump? Right, yeah, no. So just so we know, these are some of the components. So when we do it, it will become more obvious. But VM port groups, okay? So when we create a switch, that's fine. We choose what physical adapters on the ESXi that we use to connect to the physical network. And then in order for us, the virtual machines that's on the ESXi servers to be plugged into that switch, we basically have to create some ports. So this is a physical switch of what I'm showing the class now. And obviously this is in the physical world, you have ports. No problems. We all know that we plug in our computers into the ports to get them on the network, right? So when we create a virtual switch, it's just a virtual switch. No ports. There's an uplink port to the physical network, yeah? But when we want to plug our virtual machine into that switch, we must configure a VM port group. That's effectively putting ports onto the switch, okay? So it's a group of virtual switch ports that shares a common configuration and allows virtual machines to access other virtual machines or the physical network, just like any other switch, okay? So port groups is just having ports on the virtual switch. Virtual LAN, a virtual LAN, so a logical LAN, so VLAN. So you guys might have heard the term VLAN. So normally when we have a network in the physical world, if we want two networks, we just get two switches. One switch, and pretend there's another switch over here. And we plug the computers onto this switch. They are part of that physical network. We plug computers into this other switch, they're part of this physical network. As long if the switches are not connected, they're part of two different networks, aren't they? That's actual LANs, two different actual LANs. But what if you only have 10 computers? Obviously, this switch I'm pointing at here has 24 ports or more. Actually, it's probably 36 ports. Okay? So if I've only got 10 computers, but I want them on two different networks, it seems like a waste to get two 36-port switches and then have only 10 computers or 5 on each switch. It doesn't matter. So what VLANs are is that we can actually go into the configuration of the switch and create virtual LANs. So we actually split off these physical ports into different LANs as if they're on two switches. Okay, that's what VLANs are. They're not actual because they're not on the different physical devices. They're virtual because they're on the same physical device, but you're just through configuration separating it. So virtual LAN is a logical LAN that's configured on a virtual or physical switch that provides, so take notes, virtual or private, physical. So we've been talking about physical because we all understand physical, but in the virtual world, it's the same. We can create VLANs as well. Okay, so that provides efficient traffic segmentation. So that's the reason for having VLANs, is to segment traffic. Why? Maybe for security, maybe for broadcast storms, or maybe for other reasons. Like I said before, here at TAFE, we have a different VLAN for each of these classrooms. So what we do in this classroom doesn't affect what other people do in other classrooms. We have VLAN for the lecturer network. We have a VLAN, or not VLAN necessarily, network for the lecturer network, a network for the server network, and a network for the Wi-Fi, network for the students. So for all these reasons, we could use VLANs. All right, so yeah, so trunking ports. So we talked about, you guys know trunking ports. What's a trunking port? Can you give me your description of what a trunking port is?
So like when we need configure like communication, like routing.
No, not routing. It's got nothing to do with routing. Routers don't get involved here.
Different VLANs to communicate.
So okay, let me just help you out a little bit. Okay, so basically trunking ports is what you connect two switches to. All right, so like I said, if you've got this switch here, and I've got another one here, if I want this switch to be connected to this switch, then I use, I don't know, one of these ports. Let's say one of these fast Ethernet ports, or gigabit ports, whatever the port might be, and I plug in the cable and I plug into the other switch. Then if I configure that port to be trunking and the port that I've plugged into the other switch to be trunking, that means that they can allow the VLAN tags to flow from one switch to the other switch. So we can actually combine these two physical switches into one big physical switch, if you like, and still have the VLAN information across both. So a trunking port on a physical switch that listens for and knows how to pass traffic for multiple VLANs. So if I've got VLAN 1, 2, 3, 4, 5 on one switch and got VLAN 1, 2, 3, 4, 5 on another switch, they can still have the same VLANs on different switches, and they can still regulate the traffic between them. Okay, it does this by maintaining the VLAN tags for traffic moving between the trunking port, trunk port to the connected devices. Trunk ports are typically used for switch-to-switch connection to allow for VLAN to pass freely between switches. Virtual switches support VLANs, and using VLAN trunks allows the VLANs to pass freely into the virtual switches. So key point there, so hopefully you guys understand what VLANs are and trunking ports, but the virtual switches that we'll be creating is also capable of VLANs, and therefore trunking ports. In fact, when we create a VLAN in our virtual switch and we uplink it to the physical network through, obviously, the network card on the ESXi server, so this cable plugs into the room, plugs into wall, goes through the patch panel, comes out of the patch panel, plugs into the switch, and if it's plugged into switch port 1, then we need to make sure that that switch port 1 is configured as a trunking port, so that the VLANs in the virtual switch can communicate with the same VLANs that's on the physical switch. So the VLANs can flow from physical to virtual, or virtual to virtual. Okay? Same way you understand what trunking ports are is the same way. What about access ports? So access port is a port on a physical switch that passes traffic for only a single VLAN. But unlike a trunk port, which maintains the VLAN identification for traffic moving through the port, a access port strips away the VLAN traffic and moving through the port. So this is a normal port, if you like to think of it. The trunking port maintains the VLAN tags, but normal port does not. It's just for normal single machine access. All right, so network interface card, or NICs, teaming. So you understand the term team, right? Team is we're friends. We work together. We're working together to achieve something. Okay. So if you have multiple network cards, they can be teamed together, and the aggregation of physical network interfaces to form a single logical communication channel. So there's a couple of words there that you guys, a lot of people might not be able to understand. Aggregation means put together, combine, and communication channel. Basically, it's like we use communication across all the NICs for the same purpose. So if you have 1 gigabit NIC, if you have 3 of them, it gives you 3 gigabits when you combine them together, isn't it? So you increase the bandwidth. The other benefit is if you have 3 network cards doing the same job, if one of them fails, physically fails, the cable gets unplugged, or something like that, you still got the other 2 to still work, don't you? So it provides a level of fault tolerance as well. So basically, different types of NIC teaming provides varying levels of traffic load balancing and fault tolerance. So load balancing means you spread the load of the communication across however many NICs you have. You could, it says varying levels. So you've got different types of NIC teaming. You could have it where it's only 1 active and 1 passive. So you're still just using 1, so you don't have any load balancing powers there. And so therefore, that's only for fault tolerance. Where this fails, this one takes over. Okay? But you can also have it so they're both active, so that there is load balancing. And then still, if one fails, you still got another one, but at half capacity. VMX net adapters. So I think this shouldn't be a big deal for anyone because we've been using virtual machines for so long now, right? So when we create a new virtual machine, we give it a network card, and basically it's a virtualized network hardware and adapter. So it's a virtualized network adapter operating inside the guest operating system. Well, you guys understand when I say guest, right? What's a guest?
It's like this virtual machine.
It's a virtual machine, isn't it? Okay, so if we're talking about VMware, vSphere, in the worksheet 1 or 2, you created Which Server 2019, right? And you have the ESXi. Which one's the guest? Server 2019, that was inside of the ESXi, right? So that's the guest operating system. When I say host operating system, which one's that? ESXi. So this is a term that we know from Cert 4, okay? So when I use the word host or guest from now on in my writing, in my language, you should know this. Okay, so I'm making sure that's clear right now so that we don't have any confusions in the future. When we're talking about the guest, we're talking about the virtual machine that's running inside of ESXi. Because in reality, there's no VMware workstation, is there? This is just an easy teaching tool. When we're talking about guest operating system, we're talking about the virtual machines that's in ESXi. When we're talking about the host, we're talking about the ESXi host. Okay. So the VMX net adapter is a high performance 1 gigabit virtual network adapter that operates only if the VMware tools has been installed. So we know about VMware tools. The VMX net adapter is sometimes referred to as the para-virtualization driver. The VMX adapter is identified as flexible in the VMware VM properties. There's also a VLANs adapter. It's a virtualized network adapter operating inside the guest again. So these both are virtual adapters. The VLANs adapter is a 10100. Okay. that is widely compatible with a range of operating systems that's default adapter used for it until the VMware tools is complete. So obviously, why do we even have the 10100? It's to provide backward compatibility to some of the older operating systems. Not that it'll come up once, but the E1000 adapter is similar to what we get in the VMware workstation. It's a virtualized network adapter that emulates an Intel E1000 network adapter. So you know why that's easy? Well, the operating system already has the built-in drivers. No need to have, when you create a virtual machine, have you ever need to install drivers? Never, right? Because they simulate or they create the virtual hardware that has the drivers already. So this is the one we use normally in our normal VMware workstation. So that's an Intel 1 gigabit network adapter card and is the most common for 64-bit virtual machines. So putting together virtual networks, so this is the complicated part. This is the part where you have to fully understand why we have different networks. How many networks do we need? What, do they need to be separated? Can they be combined together? Do they need to have, how many physical network cards do you need on your host to achieve this? So we need to answer the following. Do you have or need to have dedicated network for management? So if you remember what management is, if this is the ESXi host, and I have a computer sitting here, and I use my computer to manage it, open up the web interface. You seen that, right? I can only do it from the management network. Okay, so I have to decide which one is my management network. If I, for example, in TAFE-SA, if I make the management network the same as the student network, that means every student could possibly manage my ESXi. That's possibly a security risk, isn't it? So normally the management network is selected only for a network that's secure. Maybe the lecturers network, maybe the server network, maybe the admin network, whatever you want to make sure it's secure. Okay. Do I need a dedicated one? If you have a small organization, maybe that you don't need it. If you have a large organization, you probably do need it. So the next one is, do you need a dedicated network for vMotion traffic? Okay, so remember in order to have vMotion, the live migration for a virtual machine between one host to another host without downtime, we need a special network that transfers that information, right? But what you're probably thinking, why can't we just use the same network as my other network? Well, you can. So if I have all these clients, all accessing the server that's on this ESXi host, accessing it through this one cable, then I do also vMotion through that one cable, you can imagine there's going to be competition for traffic bandwidth, isn't it? So if you have very little amount of clients, probably good. But if you have large amounts of clients and your servers are very busy, services in the host, the guest virtual machines that provide services to the clients, if they're very busy, maybe that's going to be too much of a disruption. So maybe you need a separate network for vMotion. Do you have an IP storage? Is the IP storage network dedicated network? Are you running iSCSI, NFS, or NAS? And we'll talk about that next lesson. But we've already sort of spoken about it, haven't we? But we said that for vMotion to work easily, just the normal vMotion on the storage vMotion, we need to have shared storage. Okay? So shared storage is storage that's not on any one ESXi server. It's on a separate server, whether that's a SAN, whether that's a NAS, whether that's a fiber optic, what's a fiber channel, iSCSI, fiber channel over Ethernet, NFS, whatever. It needs to be a third computer to provide storage. But again, we have to think about it. If the virtual hard drive is sitting here, but the virtual machines are running here, it obviously still needs to read and write from the virtual hard disk, doesn't it? So every time it reads, it goes through the network cable, goes over here, reads it, brings it back, and uses it. And every time it needs to write, it needs to do the same thing. Well, that means that storage network is going to be very, very important for your functionality. If it's slow, then you might mean that your virtual machines are slow, even though this computer's got plenty of resources. So again, the question is, can I share with any other type of communication? I'll probably say no. Okay, so the probably two important ones are the storage and the virtual machine traffic. The vMotion might be able to combine with fault tolerance, high availability as well, because they're not always used. Okay, vMotion is not 100% of the time, is it? It's only when we need to. The fault tolerance is not necessarily, the high availability is not 100% of the time either. It's only the heartbeats mostly. So how many ESXi, how many NICs are standard on your ESXi host design? So when you go out and buy a piece of hardware that you're going to send into ESXi host, how many network cards do you get? Can I have separate network for VM, separate network for storage, separate network for management, separate network for vMotion, separate network for whatever? If you don't, you maybe need to buy expansion cards. So I'm sure you've seen that. You can actually buy cards with multiple NICs and plug into your server, or configure a server that's already got that. Let's see if we can find one. Let's close this. All right, so if we look at images, so this is the expansion cards, for example. Okay, you can see that this one expansion card, PCI Express, you plug it into your server host, like a host, your ESXi host, and then that gives you 4 more network cards, doesn't it? When you buy 5 of these, it gives you, this is 4, so it gives you 20 different network interface cards.
And you don't need a switch.
No, you do need a switch, because each one of these has to plug into a switch somewhere, okay? Because they have to be uplinked still to the physical network. So that's what I mean. So it's not like, oh, I've only got 3 network cards on my server, so I must only somehow get to work with 3 network cards. You can definitely configure your server with multiple network cards, or you just buy servers with that in mind already. So let's go back to that thing. All right, so do the NICs on your host run 1 gigabit? Okay, gigabit is pretty normal, isn't it? Even all of these computers have gigabit. But if you think about it, if you have a host with 5 virtual machines on there, which has 5 servers providing services, they're going to be a lot busier than a normal client machine, aren't they? But if we have 5 servers and there's only 1 network card you're going through, and that's 1 gigabit, it's like 1 gigabit divided by 5. You're really getting 200 megabits per server if they're all using it equally. Is that enough? Okay, so that's a question. Is that enough? If it's not enough, we talked about NIC teaming, so we can add extra NICs, just like we said, or we can just get more faster NICs. So hopefully in your Cisco, you will already learn about these faster network interface ports on your backbone networks and so forth. So if you get a 10 gigabit Ethernet card on your servers, you can obviously plug them into the fastest switch ports that you need to access. Is there a need for extremely high levels of fault tolerance for your VM? So how important are your VMs? So you'll realize that once you have all this basic infrastructure set up, the most important thing is to maintain the uptime of your services. Okay, uptime. So obviously, when we're talking about fault tolerance, it means if something breaks, it still can operate. So if you have 0 fault tolerance, one thing breaks, no more service, which is bad, right? Our job is to maintain that uptime. So the more fault tolerance you can have, the better. But obviously, the more fault tolerance you can have, the more complicated it is, and also the more expensive it is. So how long is your piece of string? How much is your budget? What is your requirement? You probably in your Cert 4, you talked about, in your cloud subject, you talked about the 5 nines, 99.999% uptime. So you can't achieve that just by having no fault tolerance. So think about that. Is the existing physical network composed of VLANs? So do we already have VLANs in our physical network? Okay, maybe not. So if we're talking about the Earthies confectionery one that you see in your assignment, I can't remember. I think there's just one big network, physical network, isn't there? Maybe you should have VLANs. For that simple network, probably there isn't. Do you want to extend the use of VLANs into the virtual switches? Okay, that's important. So if you've got VLANs in your physical world, do you want VLANs in your virtual world? or are the virtual servers all on the same LAN anyway? So now that's interesting. Maybe I'll have some servers which is for the internet, some servers which is for the WAN. Well, maybe they're on separate VLANs on the physical world. So therefore, in my virtual world, they must be also on separate VLANs. Okay, putting the network together. Before setting up a virtual network architecture, you need to understand the physical network components and the security needs. A successful network combines the physical network cards and the physical switches. So here's just an example. We've got this ESXi host. There's the word host. These are Windows and Linux, Windows Linux virtual machine guest operating systems. And we've created two standard switches, virtual switch 1 and 0. And you've got 4 network cards. There's 2 physical network switches, and you got a SAN, storage server. It's a iSCSI SAN. So therefore, maybe we have these 2 network cards. NIC team together. They're plugged to this virtual switch, and they're connecting to the storage server. And then these operating systems are running on this ESXi server, but their virtual hard disks are stored here. You get me, guys? That's one way. What's to say that maybe this virtual switch, this network card is plugged into this physical switch, this network card is plugged into that physical switch, and then both of these physical switches are connected to the SAN. You're probably thinking, what about these other ones? Maybe this one is connected to this one. This one's connected to this one. This one's connected to this one, and that's also plugged into the production network where all your clients sit. Whoa! So we've got storage network and production network both on the same switches. Well, this is where we can VLAN, can't we? We can VLAN some of the connections to the production network where the clients are, some of the network to the storage. That's where you start having VLANs. And obviously, if we have one here and one there, it means it's instead of just a single failure of the switch, of network card that we're protecting against a single point of failure on the actual physical switches as well. You get me? If both network cards are plugged into this one, and if this switch fails, that's still the single point of failure, isn't it? You guys understand me? All good so far? Any questions? All right, so basically what I'm trying to emphasize is that when we have this virtualization infrastructure set up, the most important thing afterwards is all about uptime. The more you can do to provide fault tolerance and eliminate single points of failure, the better your network is going to be in there. The vSphere standard switches, so that's what we had in that picture before. Standard switches is managed through the vSphere client, through the CLI or the vSwitch config command, or by operating within the VM kernel. So vSwitch virtual switches provide connectivity, provide communication. So we all understand this. Our virtual machines need to communicate with each other, with the physical world, and with maybe other things like vMotion, storage, etc. But that's what the virtual switches are for. Virtual switches alone, obviously, you can create the virtual switch, but they can't do anything until they have uplinks. Okay, especially to the physical world. So you know, there's many physical switches, virtual switches, as you like in there, and they can provide communication between the virtual machines, no problems. But if you want this physical machine to interact with the virtual machines in here, you must provide the virtual machines with an uplink for the virtual switches into the physical world. Think about our bridge network on a VMware workstation. So basically, wherever we create one of these switches, we can choose whether it's host only or bridge. But when we say it's bridge, which uplinks, which network cards we uplink it to or bridge it to. So this is an older picture, but if you look at this diagram, we've got this virtual switch 0, and we've got port groups, VLAN 19, 18, 17, and we've got these ones. But you notice that these VLANs don't have IP addresses, these switch ports. No IP addresses. They're virtual machine ports. It's just like these ports. You don't give these ports IP addresses, do you? You just plug a computer in there and they're part of the network. So these ports are intended for virtual machines to be plugged in. Okay, just like a normal switch like that, no IP address is required. But we do know that some of these functions do require communication, doesn't it? So if we look at this one, this is the management network. Remember I said this is the network where someone can use a management interface. Obviously, in order to manage, go to the management interface, we put in an IP address or URL, don't we? So this is what we call a VM kernel port. So VM kernel, that's actually the core of the operating system, isn't it? Kernel, you heard of that kernel? Kernel is operating system. So when we say VM kernel, that's the ESXi OS. The ESXi OS needs to communicate. The ESXi OS needs to provide management, so you can either interface with the OS to manage the ESXi. The ESXi OS, this is another VM kernel port. You notice it's got an IP address as well. This is for fault tolerance, FT. This one's for VM kernel port as well. This is for vMotion, and it's got an IP address. And if you look at it, they're on separate networks, like we talked about just before, separating the traffics. All right. So if we have these separate networks, they're probably on different VLANs as well. So just key point here is the VM kernel ports are how you communicate with the ESXi, and that's why they need IP addresses. They use these ports for vMotion communication with other ESXi, for management with the admin computer, or for fault tolerance with other ESXi hosts. You see here, these are the physical adapters on the ESXi host. VMNIC1, VMNIC0. If we have 20 of them, there could be VMNIC2, 3, 4, 5, 6, 7, 8, 9, whatever, okay? But we've chosen these two. These are the first two, VMNIC0 and 1, as the uplinks. So at the back of our ESXi, these cables that are plugged into the first and second network interface cards are uplinked to a physical switch, and all of this communication goes through these two physical network interface cards. You get me, guys? Understanding? Following me so far? All right. So basically, without these, so these port groups are different VLANs for different types of virtual machines. These VM kernel ports are the ports that provide communication for the ESXi host for some function. Okay, so the way we treat a virtual switch is almost the same as how we treat a physical switch. Our understanding of a physical switch, that's why I keep on going back and forth here, talking about the physical switch. The things we think about the physical switch, we can think the same of the virtual switch. So virtual switches in ESXi are constructed by and operated in the VM kernel. So we're talking about the operating system, the ESXi operating system part. The virtual switches are not managed switches, so they're not smart, they're dumb. Okay, they're just basic switches, not this routing switches or layer 3 switches or anything like that. They're just basic switches. Yeah, and do not provide any advanced features of some of the fancy new physical switches. Some similarities, they all work on layer 2, so you know that. They all use MAC address table, easy. They forward frames from one switch port to another switch port based on the MAC addresses. Still the same, no problems. They support VLANs, no problems, understand that. They also, they can trunk by using the IEEE 802.1q VLAN tags. So we talked about the trunking ports before, right? So they pass the VLAN information from the virtual switch to the physical switch. They can establish port channels. What does that mean? That means where we can actually have multiple ports working together. Differences. So there's some differences. So virtual switches does not use dynamic negotiation. Okay, so they don't negotiate with the thing to make trunking ports. So no dynamic trunking or port aggregation protocol that you can use. You can't use those two. Okay, so you configure the trunking and that's it. There's no dynamic negotiation. A virtual switch cannot be connected to another virtual switch. Okay, because like in real world, why would you connect one switch to another switch? Is because you want to make it bigger, don't you? In the virtual world, well, it's unlimited, isn't it? You've not got fixed ports. You can just make more and more virtual ports. So there's no need to uplink one virtual switch to another virtual switch. And there's also no switching loops. So there's no need for spanning tree protocol. So there's no such thing. A vSwitch authoritatively knows, so that means it definitely knows, the MAC address of the virtual machines, because it's all part of the same system, isn't it? They don't need to learn it. You know how a normal switch learns the MAC addresses when you turn it on and stuff like that? You don't need to, because it's already there. Traffic received by the virtual switch on one uplink is never forwarded out of another uplink. Remember we had the two network cards? They might be plugged into the same switch or the same physical network. So if they receive out of this into this port, they never send it out of another one. So you can't cause loops. A virtual switch does not need to perform internet group management protocol. So it doesn't use the IGMP snooping because it knows the multicasts of all the virtual machines. Ports and port groups. To help distinguish the difference between different types of communication, ESXi uses ports and port groups. A virtual switch without any ports or port groups is like a physical switch with no ports. Pointless, isn't it? Can't do anything. A port group differentiates the different types of traffic passing through the virtual switch, and it also operates as a boundary between communication. If you're part of port group 1, you can't communicate with port group 2. Okay? And because they might have different security policies for this group of ports and other different policies for another group. So ports and port groups. So here we have 3 port groups, so VM kernel port, a virtual machine port group, and another virtual machine port group. When we see virtual machine port group, basically that means these virtual machines can use these virtual switches. So there's 2 of them. So these are different port groups, and this is VM kernel. Remember what I said about VM kernel? VM kernel port allows the ESXi host port to communicate. It has an IP address. So now we have one virtual switch. They could all be on the same virtual switch, and they've got 4 NICs now. They could all be load balanced or NIC teamed, and physical switch. They can all go into the world. But they can all have different VLANs between these virtual machine port groups, and so forth. So if we look at this, you can create a virtual switch with both connection types on the same switch. So we've got multiple different types of port groups here. We've got some for virtual machines, some for virtual machine VM kernel. And that's what I was saying before. Understanding uplinks. So a virtual switch cannot communicate with the physical world unless it's uplinked, plugged in to the physical world. So virtual switches must be connected to the ESXi's host physical adapters as uplinks in order to communicate with the rest of the world. Makes sense, doesn't it? How does it jump from the virtual world into the physical world unless it uses the physical network card? Unlike ports and port groups, uplinks aren't necessary to require for a virtual switch function. So here, this virtual switch, for example, no uplinks. That's fine because its only purpose is to allow for this internal communication between these 2 virtual machines. That's equivalent to our host-only virtual network, isn't it? Don't forget, when we say host-only and bridging, they're still virtual networks on our on our VMware workstation. Understanding uplinks, a vSwitch or virtual switch bound to at least one physical network card allows for the virtual machines to communicate with the physical servers or VMs on another ESXi host. So because these are on physically 2 different hosts, you can't use an internal network, can you? You must go through the physical network to talk to the other virtual machines. A virtual switch can also be bound to maximum 32 physical network adapters. Don't worry about the number, because every time there's a new version change, the numbers might change, because obviously, it's just like amount of RAM you can have on a virtual machine, Okay, always changes based on different versions. But in this case, you've got two physical network adapters as uplinks for the same virtual switch, and they're plugged into this physical switch, and you can see it's represented like that. Okay. Benefits: load balancing. If they're both 1 gigabit, now you've got 2 gigabit. Other benefit is one of these network card fails, that one takes over. Or, if you like, so I think the VLANs doesn't matter here. We can pass VLAN through one of them if they're configured as trunky anyway. Okay, the management network. Okay, so we talked about the management network. The management traffic is where you use a client, you open up the website for configuration. That's the management, okay? But it can only manage that ESXi server if you are connected to the management network. So the management network of the ESXi server has a VM kernel port because you're talking to the operating system, aren't you? That's why it's got an IP address. You put an IP address in, you put your username, password in, and you get in. So the VM kernel port provides network access for the VM kernel TCP/IP stack, which is a separate, independent from the network traffic generated by the virtual machine. So when we have VM port groups, that's for the virtual machines on the host to use. When we have VM kernel ports, they are for the ESXi themselves to use. The ESXi management network, however, is treated a bit different to regular VM kernel traffic in two ways, because it's always there, at least one. Obviously, if it's not there, you can't do anything, can you? So when you install it, it's there. Okay? When we use the DCUI, that's when we actually sit in front of the ESXi server, just a command line thing. You can't do much. You can use that to change which one is the management network. Okay? We can reconfigure the management network to, but not any other network. That's all we can do. So here it is. So configure the management network, and this is our IP address, and we can actually tell it, also configure which physical network card is actually doing it. So this is what I'm talking about with the DCUI. Configuring the VM kernel networking. So VM kernel networks carries management traffic, but it can also carry other forms of traffic. Just think every time the ESXi needs to communicate itself or some of the functions, it is using VM kernel. Okay, port. So some of these things include shared storage, the vMotion, the tolerance, the high availability, all of those things that we talked about, those special features. That's not the VMs talking, are they? It's the ESXi servers talking to other ESXi servers or talking to the vCenter. So all of these things, management, fault tolerance, vMotion, storage, etc., uses VM kernel ports, and they in turn have IP addresses. Okay. In this case, you've got a storage which is on this virtual switch, and that's a thin line, so that's actually uplinked to this particular network card onto the IP storage layer. This one's for vMotion, is actually using this network card to uplink to the vMotion layer. So they got separate networks for these functions, separate network cards, so we don't actually compete for the same bandwidth. VM kernel networking. VM kernel port actually comprises of two different components: a port to the virtual switch, and also a network interface, a VM kernel network interface card known as a VMK-NIC. VM kernel network interface card. That's why it's got an IP address. Creating a VM kernel port using the vSphere client combines those two parts, creating a port, creating a NIC at the same time. A VM port group, so virtual machine port group now, has a one-to-one relationship to an interface. Each VM kernel network or VMK-NIC requires a matching VM kernel port or on a switch. A VM port does not have a one-to-one relationship and does not require an IP address. A virtual switch with a VM port group acts just like an additional unmanaged physical switch. You need to just plug it into the appropriate uplinks and we'll connect that virtual switch to the rest of the network. Okay, So I think we sort of described that already. So this is a production LAN, and that's plugged into the uplink to the production physical network. And if we have any virtual machines that needs to communicate with that, they will get a network card that will be plugged into this port group and can talk. Don't forget, your virtual machine doesn't have to only have one network card, does it? You can have multiple network cards to your virtual machine, so they can be part of multiple VM ports, should I say, groups. Configure VLANs. So VLANs is a logical LAN that provides efficient segmentation for security and broadcast control while allowing traffic to share the same physical LAN segments or physical switches. VLANs utilize the 802.1q standard for tagging and marking. So what does that mean? If I receive a traffic on port 1 and port 1 is part of VLAN 1, then all my traffic is tagged with VLAN 1. And if I go from one switch to another switch through this trunking port, that tag is maintained. So I can have the VLAN 101 computers here and the VLAN 101 computers here talk as if they're on the same physical network, and then the VLAN 100 and the VLAN 100, they're talking as well. But all the other machines won't hear their conversation, won't get their conversation, won't be able to talk to them because they're separated. Okay, sorry, I missed something. VLAN tags, also known as VLAN IDs, is a numerical value, so we use numbers. Okay. VLANs impact the number of virtual switches and uplinks required. So if you think about it, if we don't have VLANs, then we, instead of actually the picture before, here, if we don't have VLANs, then instead of having one virtual switch, we would have to have one switch here, one switch here, one switch here, one switch here. We've got 4 different virtual switches, haven't we? And that's the same in the real world. If we don't have VLANs, instead of having one switch, we would have 4 physical switches. So that's the benefit of VLANs, is to actually number of physical switches you need, a number of physical cables you need to uplink. And if we look at this picture, so if we didn't have VLANs, we would have the 4 switches, 4 network cards at least, 4 physical switches at least, if there's no such thing as VLAN. You can see that's a bit of a waste, isn't it? With VLANs, we can combine, let's say, the production port group and the test development port group. So if you don't know what test dev means, it means just like the production is where the real network is, where real clients is. The test dev is where you practice. So for practice, we don't need a different physical network just so we can practice a little bit. We just make a VLAN for our practice, separated from the real client network, and then we can still do our practice without interfering with the clients. So that's one way. Configuring VLANs. So VLANs are created by configuring different port groups within the vSwitch. So during the configuration of the virtual machine port groups, we specify VLAN. There's no one-to-one relationship. A port group can be associated to only one VLAN at a time, but multiple port groups can be associated with a single VLAN. So what does that mean? Here, let me see. No, not there. Okay, here. You see how this has got VLAN 19? This is the name, by the way. It's called VLAN. That's the name. It can be named Bob if you wanted to. The name makes no difference. It's when you configure the VLAN ID here, that's where it makes a difference which VLAN it's on. So we've got VLAN 19, VLAN 18, VLAN 17. If we call this server lecturers, students, it will be the same thing. Okay? But we can configure the VLAN ID here, and that separates them. Okay. All right. Okay, so I think we're up to here. For VLANs to work properly, the uplinks for the virtual switches must be connected to the physical ports, and they must be configured as trunking. okay, trunking. So later when we actually try to connect our virtual switches to the TFSA network, and we're going to configure VLANs, do you think it's going to work or not? Yes, no question. Vote. Do you think it's going to work or not? Yes or no?
Yes.
Yes. What about you, Robin?
Yes.
Alexi says yes. What about you, Roman?
I think so.
You think so too? I think no. You know why? Do you think we can configure the TFSA switch? Did you configure the TFSA switch today?
No.
No.
No? Did you? No. Did you configure the port you're plugged into as a trunking port? Did you? No. So if it's not configured as a trunking port, our VLANs does not go to the physical network, does it? We have no access to the physical TFSA port, switch, do we? So obviously this is a classroom environment, we shouldn't have access. But just as long as you understand why is not my VLAN traffic not getting to the physical network, it's because we have not configured the physical port that we're plugged into as a trunking port. You get me? If it's not done, then VLAN traffic is not passed through. Remember back to almost the first part of the lesson, do we know what trunking port is? Do we know this stuff? And because of that, that part won't work. Within the virtual machines, obviously it does work, but until we can have access to the physical switch, then it won't work. Yeah, so a trunk port understands how to pass the traffic from multiple VLANs simultaneously by preserving their VLAN IDs. So all we're plugged into is what's called a normal access port. Access port, if you remember, just strips away the VLAN IDs. What about NIC teaming? So we said NIC teaming is where you got multiple NICs working together as a team. So here, NIC teaming involves connecting multiple physical NICs into a virtual switch. NIC teaming provides redundancy and load balancing. Let's say these two are both in a team. And obviously, if we've got, if we've got 1 gigabit, another gigabit here, when you combine them in a team, 2 gigabit. Well, now, like we said, if one fails, that one's still working, still can work, even though it's half capacity. In the physical network, you can also have redundant switches. So both of these are plugged into the same physical network. And even if one of these switches fails, you still can have communication on another switch. You're trying to eliminate as many single points of failures as possible. Configuring NIC teaming. A functional NIC team requires all uplinks to be connected to the same broadcast domain. If VLANs are used, then all switches should be configured with VLAN trunking. Yep, so you can see that this particular physical switch participates on both VLAN 100 and VLAN 200, whereas these other two only participates on one or the other. With NIC teaming, ESXi can perform load balancing for that vSwitch. Load balancing algorithm for the NIC teaming in vSwitch is balanced in a is a balance of the number of connections, not the amount of traffic. So that's a key point. So when we think about the amount of traffic, we think, oh, this is transferring 20 gigs of information through the network. So if you got 2 network cards, you're probably thinking 10 gig here, 10 gig here. That's not what they mean, okay? The number of connections is if I've got 20 connections, 20 people connecting, I'll get 10 connections here, 10 connections here. You get me? But if it happens that one of the connections on this one is transferring 20 gigs and all of these together is transferring 1 gig, it doesn't matter. It's balancing the number of connections, not the amount of traffic. Okay, so get that right. But obviously over the big span of things, it all evens out anyway. NIC teaming on a virtual switch can be configured with one of the following 4 load balancing policies. You can use the vSwitch port-based load balancing, which is the default. You can use the source MAC-based load balancing, IP hash load balancing, or explicit failover order. So let's have a look at this one. So the port-based load balancing ties each virtual switch port to a specific uplink. And and tips to maintain equal number of port to uplink assignments across all uplinks. Ensures that traffic from a virtual NIC will consistently use the same physical NIC. If the uplink fails, the traffic from the failed uplink will be failed over to another physical adapter. The source MAC now looks at the MAC address of where the traffic is coming from. Ties the virtual NIC to a physical NIC based on this MAC address. MAC-like that the virtual switch base policy, the source MAC policy is the best when number of virtual NICs exceeds the number of physical NICs. Okay, so if you've got so many virtual NICs on these virtual machines, but you only have a few virtual NICs, physical NICs, VMs are not capable of using multiple network unless it's configured with multiple virtual NICs itself. The IP hash, so the IP hash policy uses the source and destination IP addresses to calculate a hash. The hash determines the physical network adapter to use for the communication. This can allow a single virtual machine to configure to communicate over different network cards where communicating with different destinations. So this is probably the best. So if this one server is talking to lots of physical machines, it can use multiple physical network cards for the different connections. Whereas when we're talking about this this MAC address and this other one, they're all sort of tied to a single NIC at any one time. And once they're tied to that NIC, they're sort of stuck on that NIC. What about failover order? So failover detection with NIC teaming can be configured to use either link status method. So do you guys know what a link light is? Link light is? No? So when you plug into a machine, a light comes on, doesn't it? When you at the back of my computer, you can see that this is not on, but you can see at the back of your computers on the network card it's blinking. That's a link light. If that light is on, it means that I am turned on, and the other side that I'm plugged into is also turned on, and the cable's working fine. So link status uses that same method for showing you the light, but it detects whether the link is up. The failure of an uplink, so when it detects something's gone wrong, the cable is broken, the switch is broken, the network card is broken, whatever, it can then identify that the link is out. Then it will fail over to another network card. But this one cannot identify misconfiguration or pulled cables that's connected to a switch on the other device. Okay, so you're probably thinking, a link light, if I'm plugged into this switch, will it detect the cable pulled out? Yes, it will, because that's a direct switch it's connected to. What if this switch is connected to another switch and the cable is pulled out of that switch? So it still stopped the communication, wouldn't it? Because this is down the road. It's just like you driving down the road and going to the airport. Sorry, the Burbridge Road is fine. Oh, sorry, not Burbridge Road. So Donald Ramon Road is fine. So it's all clear. But what if the airport road that goes to the airport is there's a crash? You still can't get to the airport, can you? So this method doesn't detect the next device. What about the other method is beacon probing method. This also uses the link status, which is fine, but it also sends a broadcast frame across all network NICs. So if I've got 2 network cards, I send a broadcast to both. Okay, and obviously the broadcast goes through all the physical network and should come back around, shouldn't it? You get me? So if we are on a football oval, and I tell Alexi to run that way, I tell you, Robin, to run that way, eventually you're all going to come back to me, aren't you? But if you come back, I know there's nothing, no problems. But if you guys say if there's a big problem on the other side of the oval and you can't get through, then we won't see you, would I? So therefore, that's how it knows. These broadcast frames allow the virtual switch to detect upstream network connection failures. Okay, so it's like me saying, go drive to the airport, drive back, and let me know if everything's clear. if another way where you can't detect that airport road is got a problem, this way you can, because if you never come back, I know there's a problem. All right, these broadcast frames will detect the upstream network connection failures and will force failover when the spinning tree protocol blocks ports when ports are configured with the wrong VLANs when a switch-to-switch connection has failed. When a beacon is not returned to the NIC, the virtual switch triggers a failover to reroute the traffic from one failed NIC to another. So where this says reroute, it's not talking about routers here, okay? Reroute means physically switching to another uplink. So if we look at this one, this is beacon probing. So if we send a beacon out of all of these things, so these probes will go to here, and then so this one will send out here and will come back on these two, or it will come back on this one, but won't come back on that one. This one will send and we won't come back at all, would it? This one will send and it will come back on this one and won't come back on this one. So through that method, I can detect that there's something wrong here, and we'll stop using that one. Traffic shaping, so you might have heard of this term. This is where we reduce the amount of traffic, even though it's a 1 gigabit, maybe we don't want to allow the full 1 gigabit. So by default, all virtual NICs have access to the full amount of bandwidth on a physical network interface card. If contentions, the word means competition. If there's a lot of fighting for the bandwidth between the virtual machines, between whatever, if that becomes a bottleneck, as in that's a slow point, and hinders the virtual machine performance, NIC teaming will help. Obviously, increases the amount of bandwidth. Traffic shaping involves the establishment of the hard-coded limits for peak bandwidth and average bandwidth and burst size to reduce the VM's outbound bandwidth capabilities. So I can just say, you're not a very important virtual machine, I'll turn you down. You're just a DHCP server, that's all you do. I don't need, you're not a priority, I'll turn you down. Distributed switches, so far we've been talking about virtual switches. They're configured per ESXi server, so you don't need vCenter so far. Okay, you can just go to ESXi1, ESXi2, and create these virtual switches, no problems. But that means if I had the same virtual switch configuration on the ESXi1 and ESXi2, I have to do it twice. Go to ESXi1, do it, then go to the ESXi2, do it. Okay, that's 5 for 2, isn't it? What if we have 100? Okay, I don't want to do it 100 times, do I? If I do it 100 times, there's probably 99% chance I will make a mistake on at least one. Okay, then that's going to be a problem. So distributed switches, or VDSs, so virtual switches are managed per host. Virtual distributors, vSphere distributed switches functions as a single virtual switch across all associated ESXi. When I create a distributed switch, I can say ESXi1, ESXi7, ESXi10. You can use this virtual switch. Okay. Similarities: it provides connectivity for VMs, uses physical uplinks to the physical network, and can use VLANs. No problems. They're still the same. But the key difference is that I am doing the one configuration across multiple ESXi servers, and I can do this only if I have vCenter. Without vCenter, you cannot do this. Setting up a private VLAN. So private VLAN, you might have heard of this before, private VLANs, but it's basically a one-to-one VLAN. So if we look at these ones, these are computers. These are just a VLAN to the router. So each computer can't talk to the other computer directly. It has to go through just router. Obviously, router sits in between all the VLANs, or each VLAN is a different segment or different network. And the only way this computer can talk to that is go through the router, come here. You can't just go like we normally do. So private VLANs are possible only when you're using distributed switches and are not available when you're using the standard. PVLANs are a way of further isolating ports within a VLAN. For example, if you have a DMZ, do you guys know what DMZ? What's the DMZ? What does DMZ stand for?
The military zone.
Yeah, zone. Yeah, but what's the use for now?
Between your internal network and external network.
Yeah.
And separated normally
Separated
by firewalls also.
Yeah, definitely by firewalls. So what you have is usually what's in the DMZ is the servers you want to provide a service to the internet. Okay? And because it's provide connection to the internet, it means the internet can also connect to it because of the services it's providing. So there's a potential that they could be compromised. Okay? If they're compromised, then they can use that computer to compromise the rest of your computer network if it's on the same network. But if it's on a different network called DMZ, it can only compromise other computers in the DMZ. But if we then set up private networks, private VLANs within the DMZ so that each one is a separate VLAN, then even if this is compromised, you cannot compromise these other computers directly. It will still have to go through the router, and that's where the firewalls, like Alexi was talking about, can exist. All right, so private VLANs will can further isolate ports within a VLAN. For example, considering a scenario where the host, scenario of hosts within a DMZ, hosts within a DMZ rarely need to communicate with each other by using VLANs for each host. But using VLANs between for each host quickly becomes unwieldy for the number of reasons. But by using private VLANs, you can isolate the hosts from each other while keeping them on the same IP subnet. Okay, so this is, I'm not going to focus too much on this. Basically, Cisco Nexus 1000V, so we all know about Cisco switches, right? In the physical world. We all know about the command line configurations. We all know about the features, the functionality, and so forth. Okay, so we have lots of expertise in Cisco, no problems. If I have a physical network all full of Cisco equipment, then I go into the virtual world. It's not Cisco anymore, is it? It's just the virtual switches. But what Cisco has is a Cisco Nexus 1000V. The V stands for virtualized. What does that mean? I can deploy this Cisco 1000V as a virtual switch in the virtual environment. So wherever we have in the physical network can go into the virtual as well. So things like quality of service. So Cisco Nexus 1000V is a third-party vSphere distributor switch. It's built as part of a joint engineering between Cisco and VMware, modeling the same behavior in the virtual environment as your physical environment. In addition, organizations can gain per virtual machine network statistics. So some of those reporting statistics that Cisco devices can collect for you, especially if you're monitoring them for cybersecurity monitoring. Has the following major components. It has a virtual Ethernet module. Uses the VMware distributed switch APIs. So it can bring features like quality of service, private VLANs, access control list, NetFlow, that's the monitoring thing, and span from the physical network into the virtual network. So the same things you use in the physical network, you can use in the virtual network. If you're using NetFlow, the physical network to look at statistics and monitor the network, you can also monitor the virtual network. All right, so the Virtual Supervisor Module, or VSM, is a Cisco NSX OS instance running as a virtual machine. The VSM then controls multiple VMs or virtual Ethernet modules as one logical modular switch. Virtual switch security. You can configure them with security policy. So you'll see that your assignment 1, I think you go in and configure some of this stuff. You can configure them with security policies to enhance the layer 2 security. For standard switches, you can apply security policies at the vSwitch or virtual switch or at the port group level. For distributed switches, you can apply security policy only at the port group level. The security settings you can configure are promiscuous mode. You guys know what that means? No, never heard of it? So normally when your computer is plugged into a switchboard, what traffic does it get? Traffic for everyone, or traffic for other computers, or traffic only for itself? What does the switch use to determine which port it sends the traffic out? So if I receive communication in port 1, and it's for Roman, and Roman's plugged into port 48 there, which port does the switch send the communication out of?
40.
48, the last one, where Roman's plugged in. How does it know that?
Because of R.
The MAC address you're talking about? The MAC address table, the content addressable memory that stores the MAC address of Roman? Yeah, that's right, isn't it? It learns the MAC addresses and associates it with the different ports, and therefore it knows that when my destination MAC says Roman, it will send it out of Roman's port. And that's the only port it sends it out, right? So if someone's plugged into port 20, he will never see it, would he? That's good, because it reduces the chance of collision, chance of the wasting of bandwidth. But what does promiscuous mode mean? Promiscuous mode means I configure this port to be promiscuous, so instead of just getting frames that's destined for Roman's MAC address, it'll get everyone's frames. You get me? Now, what can I do with that? If I've got a monitoring computer, I can sit there and just capture all these frames and start monitoring them, can't I? Obviously, this is not for hacking, but hackers in the old days used to just force switches into a promiscuous mode by running some sort of exploit on them, clearing the MAC address table, and then forcing it to send out of every port, and then it collects information, personal information. Remember with the Wireshark, you can open up the information and look at it, couldn't you? You can literally, if you're using Telnet, which is a clear text protocol, I can use Wireshark, capture a Telnet transaction, and get the username, get the password out of it. So I can do that, but not for hacking, obviously, for monitoring. Okay, there's no point plugging a monitoring server in to a switch and you only can see yourself. Right, that's pointless. You're not monitoring anyone except for yourself, are you? We're going to actually do MAC address changes. So what does that mean? That means, remember, our MAC address, we can change the MAC address. Normally it's hard-coded into the network card, isn't it? But this allows us to change it. Okay. We can also forward transmits, so we can actually create packets, or frames with different information in there. Okay, so that's the end of the presentation.